Compare and contrast. It's ingrained into our psyche. From fashion styles to automobiles to our own body shapes, it's an intuitive form of measuring. Marketers and salespeople exploit compare and contrast to drive sales. Astronomers use it to validate their models by comparing the predicted to the observed. One of the most dynamic uses of comparing and contrasting is in the study of planetary science. Astronomers build models of how our solar system formed by comparing the characteristics of planets and postulating what conditions existed to form them. Astronomers then seek observational evidence to support their theories.
The exciting thing about planetary systems is we know very little about them. We know a fair amount about our own solar system, but very little about other planetary systems. So astronomers have built models to predict the formation and the nature of other planetary systems.
The most prominent feature of our solar system is that the planets revolve around the Sun along a common plane and in the same direction. The solar nebula must have been spinning in this direction as it condensed out. The planets also spin on their axes. This means that at some point in the formation of the solar system, this motion was established, playing a significant role in the theory of planet formation. The next thing we notice is the planets are divided into groups depending on their composition. The inner solar system, a region out to about 3 astronomical units from the Sun, is comprised of dense Earth-like planets and asteroids, which are small rocky bodies. The outer solar system is home to the enormous gaseous planets. Beyond the gas giants, but along the ecliptic plane, are the members of the Kuiper Belt, which include the planet Pluto and many other icy bodies, some of planetary size. Their orbits extend to about 100 astronomical units from the Sun. Beyond this lies the Oort cloud, a spherical array of icy objects that reaches out to about half a light year from the Sun. These two major characteristics, motion and location, play pivotal roles in the theory of solar system formation. The solar nebula theory of planetary formation has evolved by taking the observed characteristics of the solar system and comparing them with stellar formation in nebulae. This process begins with a collapsing molecular cloud of dust and gas. Consider the example of hand-tossed pizza dough. As the baker spins the dough into a disc, it assumes a flat shape, and all the dough is spinning in the same direction. The faster the spin, the flatter the disc will become.
The cloud is always swirling around, and so this core that's collapsing will always have a little bit of spin to it. And it might be a light year across. Now you're going to collapse this thing all the way down to the size of a solar system and a star. That's a huge change in how big it is. And as you know, if you're a skater and you're spinning at a certain speed and you pull your arms in, you spin faster. Now imagine you could pull your arms in 10,000 times shorter. You can imagine you would really start spinning. And this is what happens to these clouds.
This conservation of angular momentum causes the collapsing cloud to spin more rapidly. This increase in rotation causes the matter to flatten into a disk. As the disk flattens, the material in the solar nebula begins to come together, starting the slow process of planet formation.
So 4.5 billion years ago, there were no planets in the solar nebula. And so what we did have are lots of dust particles, gas particles, and these are all orbiting the Sun. And over many millions and millions of years, what happens is that they start bumping into one another. And the collisions between these gas and dust particles are not violent.
Particles begin to grow by condensation, when atoms of gas begin to attach themselves and the particles grow atom by atom. Over time, these larger particles begin to stick together in a process called accretion that's comparable to the process that forms dust bunnies underneath your bed.
They'll start to clump together. Within maybe a few millions or hundreds of millions of years, they've clumped together into tangible, tangibly sized bodies, millimeters to centimeters, and they'll interact with each other and coagulate into bigger and bigger pieces until eventually we have something that we'd call planetesimals, kilometer scale objects. And when they start to get that big, they will smash into each other more rapidly, more violently, and eventually we will accumulate a large body.
Over time, small planetesimals collide to form larger planetesimals, eventually forming protoplanets. These bigger objects are no longer homogeneous bodies of material. They contain many different elements and compounds. Heat generated in the core, either by the protoplanet's rapid growth or through radioactive decay, melts the material, which then separates by density through a process called differentiation. Heavy materials like iron sink to the center to form the core, and lighter materials float to the outer layers to form the crust of the protoplanet. These hot protoplanets continue to grow as they sweep up material along their orbital paths around the Sun. What happens next is determined by their location in the solar system.
There are some very simple indications of how to understand how planets form and evolve, especially within our own solar nebula, by just simply looking at distance from the Sun. And in particular, if you look at the solar system, you see two broad divisions. The terrestrial planets, which are small and rocky and close to the Sun, and the giant planets, which are large and composed mostly of gases and liquids, and they're relatively far from the Sun.
These gas giants are commonly called the Jovian planets, and they are enormous. For instance, over 1,000 Earths can easily fit into the planet Jupiter.
And there's a transition region between Mars and Jupiter, which we call the asteroid belt, and which in general has objects which kind of lean towards the rocky end, and as you get farther out on the asteroid belt, they tend to lean more towards the icy or colder object end of the spectrum.
This delineation between the rocky terrestrial planets and massive Jovian planets offers evidence to support the solar nebula theory.
In general, the way you can understand it is that when you're in close to the Sun, where it's hot, materials that are volatile, and what I mean by volatile is things that might be gaseous or liquid at room temperature or which easily evaporate, by definition can't condense where it's hot. And so the kinds of materials that are available to form planets in close to the Sun are things which have high melting or boiling points, things like rocks and metals. And in particular, as you get closer to the Sun, the only things that stick around are what we call refractory oxides or ceramics.
The amount of material accreted by the terrestrial planets was determined by their orbits. The 4 inner planets have smaller orbits, and therefore the amount of material available, volatile or not, was less than planets had in the outer solar system. The Jovian planets have larger orbits, and therefore had more material to accumulate.
As it turns out, rocks and metals are a very small fraction of the components of the solar nebula. If you look at the composition of the Sun, you find it's primarily hydrogen and helium, and a percent or so, roughly, of heavier elements. If you think of the Sun as forming out of a cloud of primarily hydrogen and helium with a little smattering of these heavier elements, you can imagine that as the Sun forms, and the central ball of the Sun forms, and then as the material spins out into a disk, the materials available to form planets in close to the Sun, which are rocky and metallic, are a small fraction of the total material around.
The location of the Jovian planets can help explain their massive size. Just inside the orbit of Jupiter, there existed what some astronomers call a snow line. From this point outward, the solar nebula was extremely cold, which allowed volatile materials to exist as ices. These ices included not only water, but frozen gases as well.
So it's cold enough because you're far enough away from the Sun, that the temperature is small enough that you can have the water, which is a very abundant molecule in interstellar space and in regions that are forming solar systems, in dense molecular clouds, in protoplanetary disks, and solar nebula type disks.
If you can have enough rock and metal and ice and other things around to form a large enough initial body, something that's about 10 times the mass of the Earth, then what will happen is that the hardest stuff to incorporate into planets, which is the hydrogen and helium, will get dragged into these things simply by gravitational attraction. And once that process starts, the gravity of the central object gets larger. That allows you to grab onto more hydrogen and helium, and you have this kind of runaway catastrophic effect where you pull in a whole bunch of hydrogen and helium, and if there's enough around, you can form what we call the giant planets, which are primarily hydrogen and helium, and have a core of rocky and metallic material. An example is Jupiter, which has about 300 times the mass of the Earth, and the central 10 Earth masses or so are rock and ice, and there are other 290 Earth masses are primarily hydrogen and helium.
Water ice could not only be stable, but would actually condense out of the gas phase and form essentially snowflakes. And then these snowflakes would grow to larger particles, or they would stick on rocky bodies and actually form stable building blocks of planets that have water ice in them.
The clearing of the solar nebula is the last stage in the formation of the solar system. When the nuclear furnace of the sun ignited and the sun became luminous, the pressure of the sunlight, the radiation pressure, pushed the smaller particles of dust and atoms of gas out of the solar nebula. This pressure, combined with their highly energetic solar winds, blew the majority of the lighter mass particles out into interstellar space. The planets played their part in clearing the solar nebula by acting like gravitational brooms, sweeping up the leftover debris. This created a period of heavy bombardment and took place until about 4 billion years ago. We see evidence of this as cratering on every old and solid surface in the solar system. The source of this bombardment was not limited to asteroids. Comets were also involved. These icy objects from the Oort cloud and Kuiper belt form long tails of gas and dust as they approach the sun.
The planet closest to the inner part of the Kuiper belt is Neptune, and Neptune's gravity occasionally can reach out far enough to perturb the orbit of some of these Kuiper belt objects and slowly migrate them into the inner solar system through the band of outer planets. So some of them get collected by the outer planets, but some actually make it through the outer planet region, and when they do, they work their way down into the terrestrial planet region.
When the solar system was forming, we had the solar nebula, and we had a young Earth. It was very, very hot. So hot that we couldn't get that water to condense out. So the young Earth was probably not very rich in the lighter elements like the hydrogen and oxygen that are in the water, especially the hydrogen. So the comets become a real key player in this.
The gravitational effects on smaller bodies may also have thrown them out of the solar system. The combination of all this activity eventually cleared the solar nebula. The solar nebula theory was developed over years of careful observation and analysis of our own solar system. As we observe more, we can refine the theory. In the 1990s, the Hubble Space Telescope, equipped with an infrared camera, detected protostars and protoplanetary disks in star-forming nebulae around the galaxy, giving credence to the solar nebula model. And the Spitzer Space Telescope, launched in 2003, provides even more evidence to support the solar nebula theory.
The outer solar system, which I would define as from the outer part of the asteroid belt out beyond Pluto to the Kuiper belt, is really the largest part of our solar system. It is more than 95% of the area of our solar system, if you want to look at it from that point of view. It's really most of the planetary material, the most massive planets, the gas giants, lots of moons. And so in many ways, it's the part that is best compared to disks around other stars, where we think that planets are forming. Up till now, it's been difficult, though, to actually look at that part of these disks, the part that will form the equivalent of our outer solar system, because it's cold, and so in the outer part, the disks don't produce very much light. So most of the radiation that we see from those disks comes from the inner part. But now with Spitzer Space Telescope available, we should be able to get a really good understanding of the outer parts of those disks. And so far, what we've seen is that they vary in terms of where the debris is, where the leftover material of planet formation is. The sizes, the structures of the disks vary. So there's nothing in these disks that would tell us that our own outer solar system didn't form from something like those phenomena, but it may be just one example of a wide variety of possible planetary systems expressed by the diversity of the disks.
In addition to observations of protoplanetary disks, astronomers have been able to indirectly and directly detect planets around other stars. Astronomers call these extrasolar planets, planets outside our own solar system. The detection of the first extrasolar planet took place in the mid-1990s.
My collaborator Paul Butler and I dreamed up the idea of discovering planets around other stars back in the mid-1980s, before any planets were known. People indeed thought we were crazy to imagine that we could discover planets around other stars. But we developed this technique of watching the star wobble due to a planet going around it.
The technique that Butler and Marcy developed involves observing a star over a long period of time and noting the slight Doppler shifts in the spectrum of the star. They expected these shifts would occur over months or years, like the planets in our solar system. Were they surprised?
The way we discover planets around other stars is really very simple. We watch the star itself because we really can't see the planet. It's 1 billion times fainter in reflected light than the star. Indeed, planets by definition don't produce their own energy. So we can't see the planets going around, but we do see the star wobble in space. You might think a star ought to just sit there, but in fact when a planet goes around it, the planet yanks gravitationally on that star. And so we actually see the star wobbling when there's a planet going around it. The way we detect the wobble of a star is by watching the light from a star. When the star is coming toward you, the light waves get compressed. And when the star is coming away from you, the light waves get stretched out as the star recedes away. So we watch the light waves from a star to see if they're being alternately compressed and then stretched. And that's called the Doppler effect, something we're all familiar with.
To understand how a planet could tug on a star enough to shift its spectrum, consider this dog owner with her pet tugging on her in different directions. Even though the dog is much smaller, each tug affects the motion of the owner. In stars, the tug of the planet is observed as slight shifts in the spectral lines. Although this technique seems straightforward, it took over a decade to produce any results.
And we spent many years, 6, 7, 8 years, 7 days a week, working till midnight, developing this technique. There was a Canadian team doing the same thing in Vancouver. And at the University of British Columbia, they actually implemented their technique as we were. And they tried it out on 20 stars. After about 8 years of working at it, they found no planets at all. And we learned of their result in about 1994. I went to a meeting in the Netherlands. My collaborator Paul Butler and I watched more or less in horror when we learned that this Canadian team had just spent 8 years of its existence fail to find any planets, using exactly the same idea, measuring the Doppler shifts of stars. We knew right there that we were in very big trouble. We ourselves had spent a lot of years, 8 or 9 years, working on our technique. We hadn't found any planets either. And seeing them fail too told us that we had to do better. We had to improve the precision far better than the precision we had achieved up till that point. We went back to California after that meeting in the Netherlands, knowing that we had our work cut out for us.
Although Butler and Marcy refined their techniques, they did not discover the first extrasolar planet.
So when I got this email stating that the Swiss team in Geneva had found the first planet, I figured this might well be just another false claim. Luckily, that very same week, Paul Butler and I had telescope time at Lick Observatory in Northern California. We went to the telescope, we had 4 consecutive nights, and we observed the star 51 Pegasi, which was the one the Swiss claimed had the first planet. At the end of those 4 nights, we ourselves had measured the velocity of this star by the Doppler effect, and we saw exactly the same planet that the Swiss had claimed to find. And so within a week, the world not only had the discovery of the first planet, but a confirmation by a competitive team, us, showing that indeed the planet was real. And so it was a very exciting and glorious time when suddenly, after 2,000 years since the time of the Greeks, people wondering about hunting for other worlds around other stars, we finally had the first one.
Since the discovery of 51 Pegasi, astronomers have discovered hundreds of extrasolar planets using the Doppler shift method. But this method only measures the mass of the planet tugging on the star. The planets found have been massive, Jovian-sized, and with orbits much different than those in our solar system. These observations are in conflict with the solar nebula theory.
Now, we've been finding planets. We've found over 100 of them so far. They don't fit the theory. First of all, they're finding Jupiters, which are very hard to make, inside the orbit of Mercury. Some of them have orbital periods of 4 days, 5 days, 6 days. Nobody expected that. Even worse, the orbits are elliptical, highly elliptical. That doesn't fit in with the theories at all.
The problem posed by these observations might be considered examples of extreme solar systems and not the standard. The reason is the detection method is limited to observing only those solar systems with planets that can exert enough gravitational force on the star to see Doppler shift in the spectra. This means we can more easily detect massive Jovian planets orbiting very close to their stars, where the gravitational interactions are strongest. But better, more sensitive methods and new space-based telescopes will measure smaller Doppler shifts and even detect the atmospheres of extrasolar planets, thus giving astronomers more accurate data and images.
For the first time, we detected the light emitted from the planet itself. We don't actually see any of the light from the planet directly. So we have to use a trick, which is that if we have an eclipsing system, if we have a system which indeed transits its star, then we know that exactly half an orbit later it'll pass behind the star. What we can do is to use the 3 or so hours when it's behind the star to get a very precise measurement of the actual brightness of the star, and we can subtract that from the other data. And so if you have moments of time where you're observing both the planet and star, and then you subtract the star, you're left with just the light from the planet. What we learned from these observations were a couple things. First of all, we were able to derive the temperature of the planet. So by measuring the infrared brightness, we could figure out how much heat was being emitted by the planet, and that might tell us whether certain atoms or molecules are present in the planet's atmosphere. And although we only have a very sparse data set, we just have a few measurements, we now expect to go back and use the Spitzer Space Telescope again and make many more detailed observations and really see if it varies a lot with wavelength and what that might tell us about the planet's atmosphere.
Advancements in observing techniques like these, combined with new space-based instruments, may soon reveal Earth-sized planets and their atmospheres.
I think the first big step towards finding Earth-like planets will occur with the launch of NASA's Kepler mission. The Kepler mission is going to be a space satellite that is going to do in space what we have tried to do from the ground. Kepler is specifically designed to look for much smaller eclipses, and namely eclipses due to little Earth-like planets. So when the Earth passes in front of a Sun-like star, it blocks less than a part in 10,000th of the light. And so it's a very, very tiny signal. But Kepler, being in space, being in a very stable environment, will be able to make those observations. Then beyond that, the next big step will be NASA's Terrestrial Planet Finder. The Terrestrial Planet Finder missions will directly study the light from these Earth-like planets by separating it out from the glare of the star and then perform spectroscopy on the light from the planet and look for the signatures of life in the atmosphere. They will actually be able to look for the signatures of gaseous molecules, notably oxygen, which we know on Earth is generated through biological activity. And so we think if we study planets around other stars, and they are in the right distance, the right environment from their stars, and they also have oxygen and other molecules, then that would be a pretty good hint that there might be life on those planets.
Each new discovery, whether Earth or space-based, will refine the solar nebula theory and give us a better understanding of how our own solar system formed. Astronomers have built a model of the process of planet formation from observations within our own solar system and by peering across the galaxy to glimpse dusty disks around forming stars. The dust and gases segregate by their proximity to the host star, which leads to the development of the various bodies within a solar system. Rocky small bodies form within the warm regions close to the star. Massive gas giants build up in the cooler expanses of the solar nebula, and smaller icy bodies at the outer edge. As astronomers continue their observations, some of their theories will be reinforced and some will be modified. The knowledge gained may someday lead us to discover if we are the only Earth-like planet within the galaxy, or just one of many among the stars.